At its base level, physical reality is unreadable. Look closely at any functioning system, and the flow is a jagged edge of instant, chaotic data. Measurements of the electrical discharge in a beating heart, or the energy fluctuations of a quantum field, reveal that raw physical reality is noisy and discontinuous. In 1931, logician Kurt Gödel demonstrated that this discontinuity is a mathematical law of complex systems. Gödel's incompleteness theorem states that any sufficiently complex logical system contains true statements that cannot be proven within its own rules. The system cannot close on itself perfectly. Translated into physical geometry, this means the universe contains inevitable singularities and structural gaps where the standard rules of a system break down. When a system hits one of these unresolvable mathematical glitches, it should crash. For the universe to function, physical systems must possess a shared mechanism to navigate these gaps without collapsing. That mechanism is the application of topological smoothing and renormalization. These glitches provide the necessary gateway for time, memory, and evolution to exist within a deterministic universe. Human physiology provides the clearest example of this in action. Our sensory organs function as analog calculus engines, designed to filter noise and extract stable realities. In the retina, specific cells act as edge detectors. Instead of reporting total light intensity, they calculate the spatial derivative. By subtracting the brightness of neighboring receptors, the eye ignores static data, highlighting the object's outline to detect motion. While the eyes differentiate to find change, other systems integrate to find stability. The body uses integration to handle chaotic internal variables like blood pressure. Baroreceptors detect sharp, jagged pressure bursts of a heartbeat. The brainstem integrates the frequency of these spikes over time. By calculating the area under the curve, the brain determines mean arterial pressure. This acts as a low-pass filter, ignoring noise to find the continuous trend. Smoothing allows the brain to track high-speed objects. Due to neural latency, your brain is always receiving noisy data from the past. If an athlete relied solely on visual snapshots, they would always be reacting to where the ball was 100 milliseconds ago. To solve this, the brain employs a Markovian kernel. All relevant history is compressed into a current state estimate to predict the next step. The cerebellum acts as a biological Kalman filter. It combines a prediction from an internal physics model with noisy measurements from the eyes. The brain calculates the residual error. By calculating a weighted average, it ignores noise to output an optimal trajectory. This dynamic trajectory reconstruction allows the glove to arrive at the exact intersection of the hand and the ball's future state, despite sensory blind spots. Predictive state estimation is how neurology bridges sensory gaps, allowing us to interact with a physical world our eyes cannot fully see in real time. This smoothing mechanism scales from neurology to the fundamental architecture of the cosmos. At the quantum scale, the universe calculates probabilities amidst similar noise. Physicist Nima Arkani Hamed pioneered a framework that moves beyond the complexity of standard particle equations. In the amplitudinal model, space and time emerge from a static, multidimensional geometric shape. The volume of this shape determines the probability of physical events. However, when the probability flow reaches the boundaries of this geometry, the math hits a limit. In quantum field theory, this manifests as an infinite value, a mathematical singularity providing no usable physical results. Renormalization rescales the system, absorbing the infinite glitch at the microscopic level to produce a finite value. This transforms the sharp corner into a curved edge, allowing the probability flow to move toward the next state without crashing. These sharp boundaries are unclosable corners. They provide topological degrees of freedom where new information and future probabilities enter the universe. Quantum renormalization is the cosmic equivalent of the brain's Kalman filter, a smoothing operator turning infinite glitches into finite, measurable realities. These principles of smoothing and topological gaps were mapped long before modern physics. The Sri Yantra is a geometric diagram composed of 9 interlocking triangles. Mathematically, these triangles cannot close perfectly. Tiny gaps remain at the crossing points, structural singularities acting as the geometric encoding of Gödel's incompleteness. These gaps produce cognitive and perceptual discontinuities, points where the mind cannot smoothly navigate the geometry. To bridge these gaps, ancient traditions utilize bij mantras. These are not semantic words, but pure vibrational forms. The beach mantra acts as a vibrational bridge. As a continuous wave, it provides the necessary frequency to navigate a specific geometric singularity. This acoustic frequency acts as a smoothing kernel, making the discontinuous gap traversable. This resonance entrains the brain's fractal oscillatory system, tuning the biological resonators to the frequency required to consciously cross the geometric gateway. Acoustic smoothing kernels provide the bridge necessary to make geometric discontinuity navigable without causing systemic collapse. The universe functions as an emergent, self-organizing fractal hierarchy, scaling from biological feedback loops to quantum geometry. Benoit Mandelbert's work on fractals shows that the glitches of a system, the infinite detail and unclosable perimeters, are its defining characteristics. All these systems, the baroreceptor reflex, the Kalman filter, renormalization, and acoustic topology, reveal a single topological mechanism. Each one is executing the same operation, bridging a gap where the math or the senses would normally fail. A system that is perfectly closed and consistent is sterile. It generates no information and allows for no change. Incompleteness, the noise and the unclosable intersections, is the prerequisite for time, memory, and evolution. Calculus, Markov kernels, and renormalization are all describing this same fundamental truth of how life and the cosmos remain steady in a jittery environment. Reality remains stable because it continuously smooths the infinite gaps within its own architecture.